All right, so we're going to skip ahead into chapter 4 of our science book. As I said, as we got closer to the end, I want to get through some major points, and this is going to be one of the final 4 lessons as a sixth grader before you can become officially seventh graders. So we're jumping ahead to chapter 4, lesson 1, and this gives us the idea of what energy is. So we're going to review a couple of the terms that we've gone through already dealing with forces and apply it to our knowledge that we're going to learn today for chapter 4, lesson 1. Once again, be sure that you read the book when you're finished going through the PowerPoint so that you can get all the information and that what you're reading, therefore, should make more sense because you've heard me explain it and talk about it, and those examples that I give you should come to mind. So the book begins with introducing us to a couple of terms such as energy and work. And they tell us there in that first paragraph that energy is the ability to do work or to cause change in something. All right, so we have to know the difference between work and energy. And if work is the ability to cause change, then we say when we do work on an object, some of your energy is transferred to that object. Well, what is energy? So go back to what we talked about before when we talked about forces. So the ability to push or pull something. So my energy that is stored inside of me can cause something to turn, to move. I push it, I pull it. That's the force that I'm exerting forward. So when I give off energy and work is done, the work is the change that happens. So notice that they give you a windmill farm in the background. Well, there's a point that they're trying to make there. So let's look at the original energy or force that causes these windmills to work. The wind is constantly blowing, and therefore the wind is carrying that energy. It is doing the work because it is blowing across through the air or through the atmosphere. The wind moving itself, that motion, wind motion, is the energy. It's the force that is going to cause something to push or pull. When I see that the turbines then move or rotate, then they are doing work. So the work happens as the atmosphere is pushing the air. The energy of the wind motion is happening. Work is therefore happening on something else because of the wind. So what the book was trying to explain there on that very first page is that energy is transferred when work is done. The wind carries that energy with it, but as those turbines are spinning, then they are going to have transferred energy. They're going to take that energy. Now, just a side tangent, what then happens is inside of those turbines is a coil of wires that spin around a magnet, and they create electricity. That's how electricity is created. And then that electricity is sent through wires to an electrical plant, and therefore they're transferring energy by using the original energy of the wind. So it's being energy is transformed from one object to the next to the next as work is being done. Let's go back to what we talked about when it comes to friction. If I wanted to move that box through the slick floor and then the carpet, I know that my energy or my force has to change. But if I don't push on the box, if my physical hands are not on that box, then I can't transfer my energy into the box. So when I move that box and I get it to move, then I know that it's my energy inside of myself, right? That I'm doing work. So when you do the work on the box, you exert your force, your energy on the box, then you're transferring some of your energy into that box because you're getting it to change. That ability to change energy is done or transferred from one to another when I do the work. So another thing to think about that we've talked about is the SI or the International System of Measurements that we use to measure energy. We talked about joules before. Now, in this case with electricity, we have watts, but watts is also just a measurement of joules per second, how much electricity you're using. When I talk about power then, which is the next section in our book, power is a measurement tool. I'm going to take that same measurement of joules, how much energy is being used, and I'm going to divide it by amount of time. So this is a rate. Rate is how much time it takes for something to be done or used. So let's look at energy in our house. Let's say that with our meter here, we can go out and we can measure how much energy or how many joules were used in our home through electricity. And if I know how many joules I use and I'm looking at April's calendar, let's say we have 9,150 joules or watts that were spent inside of our house in the month of June. Mom and dad could then calculate, or you could even calculate, how much was used per day. Because in April, it's one of our months that has 30 days to it. So I'd take my overall joules and I would divide it by my 30 days, and I'd find out that we're spending 305 joules of energy per day. Now that really doesn't impact you too much, or you're not going to really be using that too much. But when you become an adult and you're paying your bills and you find out, hey, I'm spending so much money per joule that we use every day, and we're leaving the bathroom light on all day long. Let's turn that off, and we can cut that down, and that's how we save money. Now, you're not going to be calculating these in sixth grade or on your assignment, but it is something that they ask that you be introduced to before you get to seventh grade. So now you know what power is and how to calculate it. So once again, when I look at the idea of power, it is a rate. It's the amount of time dividing into the amount of energy that we use. Now, our two main concepts that they definitely wanted us to hit is kinetic energy and potential energy. And our book starts with kinetic energy. So kinetic energy is just a simple idea of motion. If something is in motion, it's moving, then it has energy and it's moving in some way, shape, or form. So some basic examples, you go running, you go jogging, you even walk, you have motion. Inside of your body, you have motion because your heart is pumping, putting forth energy and pushing blood throughout your body and sucking it back into the heart. So it's in this constant cycle. So we have motion even when it appears that we're sitting still. Any kind of animal can have motion, but inanimate objects like a bowling ball will also have motion. We talked about rolling friction. When I transfer my energy from my arm and I roll the ball, it's going to then have rolling motion. It's going to have a kinetic energy. The jets that they had talked about, the Blue Angels flying over to give some recognition to our first responders during this pandemic. They are using all sorts of energy, but they have kinetic energy because they are moving, flying through the air. When I want to calculate my kinetic energy, then I have a very basic math equation that I was asked to introduce you to. So kinetic energy is just found by taking 1/2 of the amount when I multiply mass and I square its speed. So once again, that square, that superscript of 2, it tells me I take the speed and I multiply it by itself. Now, what I want you to understand is how that impacts it. So when I talk about kinetic energy, let's talk about the idea of playing dodgeball. Okay. So in dodgeball, I was doing some, research and found out that the average speed of a dodgeball and how much it's thrown. So we all know the size of a dodgeball, they're not super huge. So let's think about which one is going to affect the pain that's registered by my body. Is it going to be the mass of the ball or the speed of the ball, and which one impacts it more? So if I know that the average person can throw a dodgeball at 50 miles per hour, that's pretty fast. And that would make sense as to why when you get smacked in the side of the face, it stings quite a bit. But let's say that I throw another dodgeball at 50 miles per hour, but I change its mass. It's twice as big as a regular dodgeball. That would make sense to us that the larger the mass, the more the impact. However, it's not the greatest change on kinetic energy. So if I think about a dodgeball being thrown at 83 miles per hour, which is the fastest one that was recorded, but it's the same size as the original. The greater impact, the greater feel that I'm going to have is from the speed. And the reason that is when I calculate kinetic energy, speed is always squared. So the changing of the speed of an object greatly compounds its outcome or its effect, more so than if I simply just change its mass. So speed is always going to affect kinetic energy, more than the change in a mass does. So then that leaves us with the last section of our book. Once again, I'm asking you to read it. I'm going through it quickly for you. Is potential energy. And potential energy just simply means it's stored. And we can have stored energy that looks like several different things. I know that if I turn the handle on that water faucet, water is going to come forward. So there's this stored energy of water wanting to gush through, but the valve is keeping it from happening. A battery has stored chemical energy, stored potential energy inside of it. And then if I plug it into my remote then works and I can access that chemical electrical energy. A dog sleeping has stored energy. We have a puppy and he's about 5 months old and he will be laying there fast asleep. All of a sudden he jumps up and starts running back and forth through our living room. We call it, the zippies because he just kind of goes crazy. But while we're sleeping, our bodies do the same thing. We have stored energy and we're processing the meal that we had at supper time to give us chemical energy inside of our bodies. We talked about ATP when we talked about living things and animals so that we can do our daily functions. So stored energy, potential energy, is usually going to be based on a couple different things, mass and position. Our book focuses on two main types of potential energy, and they are the ones that you need to know going into 7th grade. So our first one is gravitational potential energy, and it means exactly what it sounds like. So when I look in the junior high science book, they give you this big fancy definition, but it's not something that we need to talk about because if I just know that it's stored energy according to something's height, then that makes it much easier to understand. So such as if I stand on top of a large ledge and I hold this ball, I know that as long as I hold it there, it's not moving. It is not kinetic. All I have to do is pull my hands away and gravity is going to cause it to fall. And that's gravitational potential energy. Once I let go and it begins to fall, then it switches over to kinetic. So moving is kinetic, potential, it's not moving, but something could happen if it's released. To go up that hill in this car, I have kinetic energy. When I get to the top of the hill, if I park it, it's potential energy, right? If I put my foot on the brake and I'm standing there and I forget and I suddenly slip my foot off the brake, I'm going to see what that potential energy can do because it's going to start to move back down that hill. So we have kinetic energy. So kinetic is moving, potential is the storing of it. And the higher I go, the more potential energy I'm going to have. You can prove that this summer. Go out on your bike and find a small hill, stop completely, put your feet on the pedals, and then let it roll. And then go to a higher hill and stop completely, put your feet on the pedals and let it roll. And you're going to see that your stored energy is increased because the higher you are. The higher you are, the more kinetic energy you're going to end up with as you're moving. So when I look at this example with the two skiers, it should make sense that the person in blue is going to have a greater speed in his kinetic energy because he's starting out at a higher level. His gravity is increased because he's higher up, therefore he has a higher gravitational potential energy, and it will not move or become kinetic energy until he moves. So when I talk about how I calculate gravitational potential energy, then I use the idea of weight times my height. Now, notice we didn't say mass, which we talked about previously in these lessons. So once again, let's review weight. Weight is the gravitational pull. And the reason they use the term weight is because we do measure things with their gravitational potential energy when we explore space and when we go to higher altitudes just here on our planet. It should make sense then if I'm taking weight times height and I go to the same height on the moon and let go of that ball, the gravitational potential energy would not be the same. Because once again, the gravity on the moon is about 1/6 of what it is here on our planet. Would that ball fall? It would fall on the moon. but it's going to fall a lot slower, and it would look like it's defying gravity because the gravitational pull on the moon is much less than what it is here on the Earth. The last one that our book goes into then is elastic. And you think about like your shorts or the collars on your shirts, and they have elastic in them. So we know what elastic is, but elastic in that term is just a material. Elastic, by scientific terms, is the ability to be stretched, or compressed. So when we're talking about potential, we're talking about stored energy. So it's stored energy because something is either compressed, pushed together, or it is stretched out. So when I look at a spring, any normal spring, then if I don't put any pressure on it at all, pulling or pushing, then it is at static. And once again, the term scientifically static means not moving. If I compress it, it's going to have energy. If I stretch it, it's going to have energy. Some common things that have elastic energy from being stretched is like bow and arrows. So when I take that string from the bow and I pull it back, the further back that I pull it, the more compounded potential energy that I have. It is an elastic because if I let go, that arrow is going to fly and it's going to transfer the energy. Another thing that is commonly thought of is a rubber band. Rubber bands are a perfect example of elastic energy from being stretched. The further back I stretch, the more someone's going to say, ow, when I let go. Don't ever do that. We don't want somebody to lose an eye. Compressed energy would be like this hand exercise machine. So from the wires and the way they're bent, you're squeezing it, and the more you squeeze it, the harder it is to get those two handles closer together because the spring or the coil around it is keeping it from wanting to pull. If you know about vehicles, then you know that in our suspension that we often have these springs, and those springs are compressed. It takes a machine or somebody that's super strong with some really hard tools to compress those springs when we have to replace them. Those springs are pressed together so that when we're driving, it levels out our vehicle and we don't feel as much, right? In my first car, I didn't have very good springs. It was about 15, 16 years old. And as I was driving, the springs were just shot. We have shocks and we have springs, right? And every move on the road, you could feel. So those springs are once again compressed from the weight of the car and to hold it to keep everything as level as it possibly can. So compressed energy or stretched energy is potential energy because if I release it, boom, they're going to snap back together and that energy is going to pull. All right, so that's all the main points of this chapter. It's very quick, once again, less than 20 minutes because I'm just introducing it to you and I want you to go back through and read your book. Read your book, think about the examples I just talked about, and it should make much more sense. The assignment then will be extremely easy because I give you the pages, I've explained it to you, and you'll read it, and everyone should be getting an A. So we only have 3 more lessons to go. So the assignment then is going to be given to you on Wednesday. You have access to it today, and it is due Friday by 11:59 p.m. Please don't try to submit it late. It's getting more and more complicated when people are now deciding to do some work, and I'm trying to play catch up. So once again, please know I miss all of you. I miss seeing your faces and working with you and answering your questions. As you're doing your assignment, if you have questions, please just send me a message and I'll get back with you as soon as I can. If not, have a great day.